Okay, here's the section on elastic collisions in one dimension. Okay, so we had looked at before where we said, okay, I have one mass come in, this one's at rest, all right, and they collide, and then this one stops, and that one moves off with the same speed that the first one had. And we said, oh, we would observe that, and we do, okay, or we would suggest that would happen, but we weren't really actually able to prove that. So in this section, we'll actually go through the algebra to actually show that that's what happens when these things have the same mass, okay. First, I want to look at a special case of a special case for a special case, okay. So what are all the special cases? Well, there's three special cases. The first one is it's an elastic collision. Okay, elastic means kinetic energy is conserved. Okay, that's the first reason why it's a special case. Second reason it's a special case is it's one dimension. Okay, if it's in two dimensions, these things would hit and one would go one way, one would go the other way, like on a pool table. Okay, so second reason. Okay, the other reason that this is a special case, all right, is I'm going to do this for number 2, okay, initially at rest. Okay, so number 2 is initially going to be at rest. Okay, it doesn't have to be. The algebra is a mess here, but I'm going to do this in special case so that we can show when these masses are the same that indeed number 1 stops. Okay, number 1 stops here, and then number 2 goes out with the same speed that number 1 had when it came in. Okay, so here's my before picture, here's my after picture. Okay, so what we have here is number 1 comes in, okay, number 2 is at rest, okay, the masses are different, okay, masses are different, and so they're both going to move. Okay, number 2 is always going to move. Okay, number 1, if number 1 is huge, right, if M1 is bigger than M2, M1 will move to the right. If M1 is small, okay, smaller than M2, it's going to bounce backwards. Okay, so we'll see. Okay, so for example, if you did this as an experiment, you would know the masses, you would know the initial speeds. I want to find V1 final and V2 final. So this is what we want to find, those two things. Those are my two unknowns. Okay, so I'm going to conserve momentum for my system. Okay, so that's my system, right? My system is these two masses up here. Okay, so initial momentum is just number 1. Okay, remember momentum is mv. Okay, so initial momentum is m1 v1 initial. Final momentum over here is I have number 1 moving, m1 v1 final, and number 2 is moving, m2 v2 final. Okay, here's my two unknowns. All right, whoops, there's my two unknowns. Okay, so I have one equation, two unknowns. So I need another equation. Well, since it's elastic, kinetic energy is conserved. So I have K initial. So only number 1 has kinetic energy. There's K initial. And then K final, I have two things moving. So number 1 has kinetic energy, and number 2 has final kinetic energy. Okay. Now, so here's my two unknowns, V1 final, V2 final. Okay. And also, here's my two unknowns, V1 final, V2 final. Okay, so I have two equations, two unknowns. Okay, no big deal. We've been solving two equations, two unknowns all throughout the semester. What makes this one more difficult is over here, my two unknowns are squared, and over here, they're not. So that just makes it really messy. Okay, so there's a little trick on how to solve two equations, two unknowns when one of them are squared. Okay, so I call this equation 1, that equation 2. So first thing I did is I rearranged equation number 2. I got rid of the halves, cancel the halves, got rid of the halves, okay, and then I combined like terms. I brought this one over, okay, factored out the M1, so I brought this over, factored out M1, so I'd have V1 initial squared minus V1 final squared. And then this thing is left here, M2 V2 final squared. Okay, so I just rearranged equation number 2. Okay, and then I rearranged equation 1. I brought this one over, okay, combining like terms. I factored out the M1, so there's my M1. I have V1, 0 minus that. That's what I have there. And then this thing just sits here. Okay, that stays right there. Okay, so I still have the same two equations. Okay, same two unknowns. Okay, now I'm going to factor, well, I already factored number 1. I'm going to factor this top one. Okay, now you look at the top one, that looks like from algebra class a squared minus b squared. Okay, and back in algebra class they taught you that if you want to factor a squared minus b squared, it factors as a plus b, a minus b. So I took this, okay, that, and factored it here. So a squared minus b squared. So there's my a plus b, a minus b. Okay, so I took equation number 2, factored it. This thing still sits here. That's still there. And I just rewrote equation number 1. There's equation number 1 and wrote it there. Okay. Okay. Now, I divided both of these. I divided 2 by equation 1. So I just drew this line there and drew that there. Okay. So my M1s cancel. That term cancels. Okay. The M2s cancel. One of the V's 2 cancels. So all I'm left with is I have that one. Okay, the plus term. And I have a V2 final right there. Okay. All right. So in combining equations, well, factoring number 2, in combining equation 1 and 2, I wound up with equation number 3, and I still have the same 2 unknowns. Still have the same 2 unknowns. Okay, V1 final, V2 final. Okay. But what makes it better is they're no longer squared. Okay. So now I have equation 1, okay, which has my 2 unknowns. They're not squared. And now I have equation 3 with the same 2 unknowns, and they're not squared. Okay, so what I did is I substituted equation 3 into number 1. So right here, number 1, where I have my V2 final right there, I put this. So here's equation number 1. I have M1 V1 initial, M1 V1 initial. M1 V1 final, M1 V1 final. There's my M2, there's my M2. And right here where I have V2 final, I put in that stuff right there. Okay, and now you have everything in there except for V1 final. So it's just a big mess of algebra. Okay, so multiply this out, okay, group like terms, and I solve for V1 final. All right, now to get V2 final, okay, the other thing to do to get V2 final is, okay, I could substitute 3 back into number 1. So that means here's equation 3. I'd solve equation 3 for V1 final, get V1 final by itself. Okay, whoops. And then take that V1 final, stick it right there. Okay, and if you do that, okay, so here's my equation 1. See how we can do that. Okay, here's my equation number 1 right there. So I have M1 V1 initial. There's my M2. I mean, that's my M1. And right here where I have V1 final, I put in this. If you bring this one over, you have V2 final minus V1 initial. And then I still have that M2 V2 final sitting right there. So I just did the algebra. Okay. Combine like terms. Okay. And I wind up with V2 final. All right. So using conservation momentum, conservation kinetic energy, I found the final speeds, the final velocities of number 1 and number 2. They look like this. Whoa, right there. Okay. Now, if you notice, these 2 aren't on the equation sheet. Okay, because everything on the equation sheet is a fundamental expression. Okay, these are for a special case, for a special case, for a special case. Remember what the special cases were. Okay, it's elastic. Okay, so if they stick together, this wouldn't work. So it's elastic, it's one dimension, and this whole thing was derived with that one at rest. Okay, number 2 is at rest. Okay, so Okay, maybe next semester or so when you're doing these type of problems, when maybe it's an electron or some type of maybe a proton hitting a nucleus, you're not going to remember that expression or that expression. But what you will remember, you'll remember P initial equals P final, and you'll remember K initial equals K final, and then you'll wind up getting those same things again. Okay, all right, so what I have here is I'm going to show a video where here's my M1, okay, here's my M2 at rest, and the first one I'm going to have where M2 is huge and M2 is small, okay, so M1 would be big and M2 would be small. And if I go over here, okay, I want to look at what happens to number 1 when it comes in. Well, if this one's big and that one's very small, okay, the numerator, this whole thing, that's a positive number. So that means M1 is going to keep moving to the right. Okay, now obviously M2 is always going to move to the right. Okay, this one can't bump into that one and make number 2 move to the left. So number 2 is always going to move to the right. Okay, but I just did, whoops, if M1 is huge, not only after it hits M2 is M2 going to move to the right, number 1 is going to keep moving to the right. That's what that says. M1's big, M2 small, that's a positive number, okay? The other video I'll show is for the other case when M1 is small and M2 is huge. So here's my M1 coming in, and there's M2. Okay, so if I go back up here, okay, if I go back up here, okay, so M1 is now going to be small, and M2 is big. So small number minus a big number, this whole term, that whole term is going to be a negative number. So that means that number 1, V1 final is negative, number 1 is going to recoil back. Okay, number 2 is always going to move to the right. So in the video will show that. Video will show M1 comes in, they collide, and M1 recoils back to the left. Now, for a special case of these, okay, if M1 is equal to M2, okay, so that was the one I had done earlier where these were 2 billiard balls. Okay, so if the masses are equal, all right, if I look at V1 final, okay, here's V1 final right there. This whole thing is V1 final. If the masses are equal, if M1 and M2 are equal, I have M minus M. That's what I have right here, M minus M, okay? And so the numerator is 0. So that says V1 final stops, okay? V2 final, okay, right here, okay, the masses are all equal. So V2 final, the numerator is 2M, and the denominator is M1 plus M2, the masses are equal. I have M plus M. So on the top I have 2M, bottom I have 2M. Those cancel. So that says that when the masses are equal, that sure enough, number 1 stops, and then number 2 goes off with the same speed that number 1 had when it came in. So originally, I think in the last video or so, I said, well, we can observe that happens and we expect that, but here using the algebra, we were actually able to show that. And I'll show again the video that shows these come in, same mass, number 1 stops, oops, number 1 stops, and then number 2 goes out with the same speed that number 1 has. And we'll actually do that in the lab I'll post this week. Okay, now here's another interesting problem, okay? We were doing one-dimensional collisions, okay? If these things aren't head-on, okay, that's called glancing incidents, okay? Kind of like on a pool table or in air hockey, okay? So we want to show that when the collision is elastic, okay, or I said unless the collision is elastic and head-on, okay? So for example, the previous one I did, they were both lined up, along the same line. Here, when they're off axis, if the masses are the same and number 2 is at rest, they're always going to go off at a 90-degree angle. So we can show that unless the The collision is elastic and head-on. Okay, the two particles are always going to move off perpendicular to each other. Okay, when the masses are the same, and number 2 is initially at rest. So here's my before picture, and here's my after picture. Number 2 goes off up there. Number 1 goes down that way, and we want to show they go off at right angles. Okay, so I'm going to conserve momentum. Now I'm doing this as a vector. So P initial is this picture. So I only have number 1. Okay, remember I'm not making M1s and M2s. All the masses are the same. P final is I have two things. I have the bottom one and I have the top one. Okay, masses drop out. Okay, so when I conserve momentum, that gives me a relationship between the velocity vectors. So that tells me that V1 final plus V2 final has to be equal to V1 initial. Well, V1 final is in this picture up here. So V1 final points that way. V2 final is up here, that points that way. So I'm adding these two vectors, that one and that one. I did it in this picture over here. So here's V1 final, points down. Okay, right, there's V1 final there, points down. V2 final points in its direction upward. So I have V1 final plus V2 final. Okay, and if I add those two vectors together, I get a vector that points to the right. Okay, so that puts a condition on V1 final plus V2 final has to be equal to V1 initial. Okay, so there's a vector triangle. Okay, so if I look back here, up at this picture, here's V2, here's V1, and I'm trying to find that angle. Here's V2, here's V1, and I'm trying to find that angle and show that it's 90 degrees. All right. Now, remember, we're doing this for an elastic collision. So if the collision is elastic, kinetic energy is conserved. Okay, so my before picture, I only have one of them moving. That's my initial kinetic energy. The final picture over here, they're both moving. K1 final, K2 final. The halves cancel, the m's cancel, and this gives me a condition on kinetic energy. Okay, but if I look at this triangle, this says that that side squared plus this side squared has to equal that side squared. Okay, so a squared plus b squared is c squared. So this looks like a squared plus b squared is c squared. Okay, so the only way that that expression can be satisfied is if that's a right angle. So that's the direction of V1 final. Whoops. That's the direction of V2 final. So sure enough, those are at 90 degrees. So when you have an elastic collision and the masses are the same, and the first one's at rest, and the number 2's at rest, okay, this shows that they always go off at right angles. Okay, so for example, like maybe in a homework problem, if they give you a collision, okay, if they give you a collision and maybe they tell you that that angle is 20 degrees, then you automatically know that that angle has to be 70 degrees if it's an elastic collision when the masses are equal and they're off axis.